Good morning. Thank you all for giving me the time to, or opportunity to talk to you today. We're going to talk about a little bit of geography, global water supply, and a little bit about water-stressed regions. Okay? Okay. And then we're going to talk about transporting water, introduce a term called virtual water, and then we're going to connect that all together with hydrogen being able to do something about the supply of water, but also transportation. There we go. So before we get going too far, I want you to remember two numbers. One of them is 8, and the other one is 1. And you can get them mixed up and go 1-8 if you like. Water. So I think astronauts coined the term the blue marble from space. That's because 71% of our planet is covered in water. That's the good news. The less than good news is that 98% of it is not usable. It's salt water, not usable by us. Some fish like it, but not us. And so, and of that 2.5%, only less than, it says 1%, it's about 0.5% of that water is actually accessible, usable in the form of fresh and available water. The balance of that 2.5% is ice and water that's deep underground, too deep to economically extract. And so the amount of water, the little dot there, is the component of fresh, accessible water on our planet. The big blot is all of the rest of the water. It sounds like it, but you know what? That's still a lot of water. There's the 71% is about 500 million cubic kilometers of water, and the less than 1% is still hundreds of cubic kilometers of water. To put that in perspective. About 10 cubic kilometers of water flows under the Blue Water Bridge every month. And so there is a lot of water around. So why do we have this? It's because it's not evenly distributed. We have a problem, and that's, look out here, we have so much water just a few kilometers north of us, and yet so much of the world, 2.2 billion people, don't have enough water to drink. They don't have clean water. And so it's a distribution problem. People have recognized that and thought, well, maybe we could move it. And we've seen, I don't know if that shows up there, but it's a couple of ships pulling an iceberg. The idea being, well, why don't we pull icebergs to places? Indeed, it's very expensive. It's been tried. I haven't heard about it being talked about recently, but this was something that was going on a decade or two ago, so it's not a new problem. What about pipelining water? Well, I'm going to put it to you this way. Any politician who proposes something like this will be looking for a job at the next election. There's a lot of public resistance to moving. People who have the water are really protective of it. And so there was an article in Bloomberg, it's the fall-winter issue, so I don't know if it was a month or so ago, and they talked about specifically this, transporting water. And what they pointed out, now it was Bloomberg, it was an economic discussion. And I forget the number, something like 600 million cubic meters of water are shipped already around the world for a variety of reasons. That image there, if you can't make it out, is people wringing out a plastic water bottle. And so we all know that there's all kinds of water in small amounts in water bottles, and water is being moved around. But it pales into insignificance the amount of water that is actually being moved. This guy here, Anthony Allen, was a geographer, and in the 1990s, early 1990s, he conducted a study on the amount of water that's moved, physical water, embedded in products. So think of corn. If you take a kernel of corn, you squeeze it, you'll get some fluid, and that fluid has got oil and water in it. So he refers to that as physical water in the product that we're selling. But he also realized it takes a lot of water to get a kernel of corn. And so he coined a term called virtual water, and it's embedded water. We hear that term, embedded carbon in products, for example. And so embedded virtual water refers to all of the water that went into making or producing the product in the first place. And when you think of a picture like this, that all looks really good. That's a wheat field. The virtual water is what's coming out of the irrigator. That's what he was talking about. And so when you see grain being, even dried grain shipped to some other part of the world that perhaps really needs the grain, perhaps the real reason they need the grain is because they don't have enough water to grow their own. They may have the land, but if they don't have the water, you need the land and the water and the will and all kinds of other reasons to have for agriculture. But uh, by importing the grain, in a sense, what they're importing is our water, the water that we have that they don't have. And so Mr. Allen looked at a whole bunch of products. This is a very small sampling to show the amount of embedded water, or virtual water as he called it, that occurs to produce a product to be shipped. And so over in the corner, I don't know if there's a laser on this thing, over in the bottom left, it shows a kernel of corn, because I mentioned that one. According to, and this work's been peer reviewed and duplicated, and whether the number is to four significant figures, 1,222, or if it's 1,223, forget about it. It's a lot of water. Takes 1,000, according to this, 1,200 kilograms or cubic meters of water to produce 1 kilogram of corn. Now this chart kind of makes me a little sad, and at the same time, well, not so bad, because I love chocolate. And there's chocolate at 17,000 cubic meters of water to make 1 kilogram of chocolate. So that's kind of disturbing when you think about it, never mind the conditions under which some of the chocolate, the cocoa bean is produced. But what makes me feel not so bad is the wine. The wine is over there at 109. So 100, I've been saying cubic meters, liters, 100 liters of water to make a liter of wine. So if I'm having some wine, I don't feel quite so bad having the chocolate. There it shows on the 61 cubic kilometers, so that's the amount of water that would flow under the river in 6 months. Here is what's used in the UK, and you can see, so this is a huge amount of water that's being used in Europe, and yet, as I pointed out, 7 billion people, this was a little old, this slide, but it's closer to 8 now, so 2.5 billion people don't have enough water. Now we're going to bring this into talking about hydrogen. So, you know, we've been hearing about the hydrogen economy. We're going to have the hydrogen economy within 10 years, and we've been hearing that for the last 40 years. But anyway, one of the reasons, there's a couple of reasons why people want to move hydrogen. Could be as a chemical feedstock, like is used here in our refinery, or chemical plants down the road here, or it could be used for energy, to make power or energy, or to get heat. And so we think of hydrogen as an energy carrier. Sometimes you'll hear somebody say it's an energy source. It's not an energy source. It's an energy carrier, like a transmission line is for moving electricity around. But one thing we don't really see a whole lot about, and I've done a little bit of look, I wouldn't say it was an exhaustive or even rigorous look, but how about the water piece that comes with hydrogen? And could you consider hydrogen not only a potential, a potent energy carrier, but also it could be a prolific water, and I'm using the word enabler, because we're going to be thinking of this virtual water in a slightly different way than Mr. Allen did. Back to our numbers, 1 and 8. What is this all about, 1 and 8? Well, now we're going to do we did geography, now we're going to do chemistry. So the little equation in the front, at the top, two waters plus a whole pile of energy will give you some hydrogen and some oxygen. This reaction, though, is reversible, and that's what people talk about. Oh, hydrogen, we're going to use it for energy. Because if you already have the hydrogen, it says oxygen there. Think of air. Hydrogen plus oxygen releases a whole bunch of energy and water. Now, look at this, and I'm just going to, I want to explain the 8 and 1. 2 hydrogens, hydrogen H2 is 2 grams per mole, times 2 is 4. 4. Oxygen is 16. There's a little 2 there, that's 32. 32 into 8, sorry, 32 into 4 is, or 4 into 32 is 8. That's where that's where the 1 and 8 come from. And why is this important? Because for every ton of hydrogen you have, if you convert it into energy, you are going to get 8 tons of water. And a lot of things aren't as efficient as what I'm going to describe here. If you make hydrogen with an electrolyzer, the electrolyzer that's making hydrogen with electricity is going to be maybe somewhere between 60 and, at the very best, close to 70% efficient. If you then take that hydrogen and use a fuel cell, for example, to turn it back into electricity, it's only 60% efficient. So that's 30. So the efficiency of getting the energy out of the hydrogen is between 30 and at best 40%. And we're all excited about it. Oh, we're going to get a lot of energy out of hydrogen. Well, when you look at the water, it's a totally different thing. You get all the water back. In reality, the two hydrogen, and if you make hydrogen with electricity, or the way it's done here in the Chemical Valley, it takes more like 10 to 12 because there's some losses. But when it comes to getting the water back, you get it all. This is it's chemistry. You got to have a balance. If you add hydrogen to oxygen in a fuel cell, you're going to get 8 tons for every ton of hydrogen that you process. So this is a good number to work with. But in 2021, the Bowman Center worked with Queen's University they designed what we would call a hydrogen battery. And I'm not going to go into all of the detail here because it's not important. It's just that I used the information from that study to develop this talk. And so if you take all that thing apart, and if the fuel cell over there on your right, and you ran it 24/7, if you had the supply of hydrogen to do that, it would be 125 megawatts. Now I really like one significant figure, so it's 100 megawatts. And we're going to talk about the fuel cell, because this is where the hydrogen is converted into water, energy. We have hydrogen coming in at the left, 1 ton goes into the fuel cell, out comes a whole bunch of electricity and 8 tons of water. And people are building large, they're called stacks, fuel cell stacks that can produce power at the kind of rate we're talking about here. So it's not something that Don dreamt up. So in a way, we're reconstituting water. The water that was used might have been made here in the St. Clair River, but we put a facility like this in northern Canada somewhere in an underserved indigenous community, and they would have power, and they would have access to water. And so what they're really doing, they're using oxygen that's in their air to reconstitute the water that is here. And I kind of think that is kind of virtual water. It's not the way Mr. Allen thought of it, but it seems to be virtually they're going to get the same water we have. How much water are we talking about? Let's put this into context. We can all, those are theoretical chemical equations. What's this guy talking about? That battery system that I showed, the cartoon, was the intent, or the hope was to have it built here. And so let's talk about how big it is. That fuel cell in the cartoon, if it were to run as a power plant and with the supply of hydrogen, would be 100 megawatts. To get 100 megawatts electrical out of it, after all the inefficiencies and whatever, you would need to feed it 140 tons per day of hydrogen. And what would you get in return? You'd get enough electricity to supply all of the power requirements for a community like Sarnia of 70 to 75,000 people. That's for all their drinking water, most of their potable water. It would supply all the water for the commercial and the malls. It would not be enough for the heavy industry we have, but in terms of the community, more than enough. Furthermore, it would deliver, it says 1,000 because I don't like one significant figure. It's closer to 1,200 tons a day of water. So not only would a fuel cell in a community of our size that needs the power and the water, they would get 1,200 tons a day, or more than enough water for all of the drinking and potable water needs that we have except for industry. So think of a community the size of Sarnia in some underserved area. With this kind of a power plant, they'd have all the electricity they need, and they'd have all the water they need. So this is a picture of a community in Ghana. We have our 100 megawatt or something, doesn't actually have to be that big, of course, system, and it would supply all of the electricity and maybe some for export to communities around them. It would supply all the water they need for a community in Ghana or some other place. Could be in Northwest Territories here of this size. It could be extended area. It doesn't have to be focused in a small area like the size of Sarnia, the population density. But they would have all the water they would need and all the electricity they would need coming from hydrogen. When every place you read and you do a search, you'll find the energy hydrogen is all about, oh, we're going to make ammonia out of it for fertilizer, we're going to make electricity. That's a chemical use. Or you could make electricity out of it, but you don't really see anybody talking about it in the context I'm talking about, which is as a water supply. They could do more than that though, because they have to buy the hydrogen has to get there somehow. And so what if the town wasn't 70,000, maybe it's 20,000 people of the community. What if they put in a 100 megawatt unit anyway, if they can get the hydrogen? There's a lot of issues with hydrogen, which is a topic of a different day, but if they can get the hydrogen, they would have power to sell, and they could take some of the water that is made in excess of their drinking water needs and maybe to help out with their agricultural effort. And they could, so they could take some of that water and put it over into an electrolyzer to make their own hydrogen, and that would allow them to reduce, because the water would just be going on in circles. It's part of the plant. And so in that way they could reduce the amount of imported hydrogen they need to buy. There. So in summary, we talked a little bit about global water and water scarcity, introduced the term virtual water, and then turned it kind of upside down, and we're going to include the water that comes from a fuel cell as virtual water. And then so maybe we should be thinking one of the motivations to proceed with doing work with hydrogen is not only the energy and the chemical as a chemical agent or as energy, but also the water, because there are 2.5 billion people don't have enough water. We take it for granted. Look at it, it's just there. And so when I talked a little bit about shipping water at the early on, and how difficult it is. Well, shipping hydrogen is not exactly easy either, but it could be that virtual water could be shipped with using hydrogen. That's it. That's all you get.